Hello all, welcome back. In the previous couple of lectures, we were discussing about rainfall. That is how the measurement of rainfall can be done, how can we determine the optimal number of rain gauges, and after that we have seen the representation of rainfall. That is, rainfall can be represented either in centimeter as rainfall depth or in terms of centimeters per hour or any depth unit per time as intensity. And after that we have seen how can we analyze the rainfall, how can we get the missing data if there is any data missing in the existing rainfall data. So, all these things we were talking about the point gauge data. That is, we have installed the rain gauges at a particular location, and from that whatever rainfall we are getting, that we are analyzing. Okay, so we are installing the rain gauge at a particular location, and then the recorded data or the data which is obtained from the rain gauges we were analyzing, but it is giving us the point rainfall data. How can we convert this data into the one which is a representative of a catchment or an area? That is, we need to have a methodology to calculate the average aerial rainfall, which will be a representative value corresponding to a particular area. That we will see in this lecture. So, average aerial rainfall. In hydrologic point of view, we need to have the average rainfall or the rainfall over an area. That is, I told you in the beginning itself, we will be considering an area which is named as catchment, watershed, different terminologies we have seen. So, what will be the average rainfall on a catchment? That is what we are interested from the hydrologic point of view. Rainfall is recorded at the gauges. We have seen different methods to measure the rainfall. We were having the rain gauges and also remote measurements such as satellite and radar rainfall measurement techniques. But here I am talking about the rainfall data from the rain gauges. Let us have a look into these methods. First one is the arithmetic average method, Thiessen polygon method, isoheital method, and reciprocal distance squared method. These are the commonly used techniques, conventionally used techniques for finding out the average aerial rainfall. And nowadays, by using GIS, Geographic Information System softwares, we can make use of these rain gauge data and we can go for interpolation techniques to get the average values also. Let us see these techniques one by one. First one is the arithmetic average method. This is applicable. This will give the fairly good results in the case of physically and climatically homogeneous catchments. So, we will be calculating the average rainfall by using this arithmetic mean of the rainfall recorded at different gauging station. It is a simple arithmetic average. We are having an area. Within that area, we are having n number of rain gauges and we are just finding out the average of the rainfall data which are recorded at these rain gauges. We are having a catchment like this. This is a representative picture of the catchment. And within the catchment, we are having the stream network. And for example, in this catchment, we are having 3 rain gauges. We are recording the data from these 3 rain gauges and we are having the corresponding data in the tabular form. We can get the average rainfall data by making use of the simple average formula. So, that is P bar is given by P1 plus P2 plus P3 plus up to Pn divided by n, where that can be represented mathematically by using this expression 1 by n sigma I is equal to 1 to n Pi. Here in this case, Pi is the rainfall data from ith rain gauge station. Pi will be varying from 1 to n. How many rain gauge stations are there? Based on that, I will be varying. So, Pi is the rainfall recorded at ith rain gauge in the catchment. N is the number of rain gauges present in the catchment. This is a simple averaging method. So, we are having n number of rain gauges, we are having the data from these rain gauges, we are just calculating we are averaging out the data from all these rain gauges to get the average rainfall from this particular catchment. It is a very simple method, simple average or arithmetic average. It does not account for the rain gauge distribution, whether the rain gauge number is too high or we are having a well connected rain gauges. So, there is no idea related to that. We are just collecting the data and we are getting the average, we are calculating the average value by making use of this formula. So, from that itself it is very clear that it can be applied for very flat uniformly distributed rainfall occurring areas. Second method is the Thiessen polygon method. Let us see how this method is different from the first one, arithmetic average method. So, in this method what we are assuming is that at any point in a catchment the rainfall is same as that recorded at the nearest rain gauge. That is, the depth recorded at a rain gauge is applied out to the distance halfway to the next station in any direction. In a catchment there may be n number of rain gauges and these rain gauges will be located. There will be certain distance between them. So, we will be assuming that up to half of the distance between two rain gauges we can make use of the data from one particular rain gauge. Around a particular rain gauge, what we will be doing? We will be constructing a polygon. That is why the name Thiessen polygon method. So, around a particular rain gauge a polygon is constructed and that particular rain gauge is the representative rain gauge corresponding to that area within the polygon. So, we are having a rain gauge. So, we will be constructing a polygon inscribing that particular rain gauge and that particular rain gauge will be representing the corresponding area. The whole area of the region be A. We are considering a watershed or catchment, whatever be the area, which contains a number of rain gauges, that area be capital A. So, this is a representative figure showing the catchment which is having an area A, and within that we are having different number of rain gauges present. Here I have considered 3 rain gauges. These are the precipitations from 3 rain gauges P1, P2, P3. What we will be doing? We will be joining the location of the rain gauge by straight line to form a triangle. Here in the simple way you can see these 3 rain gauges are connected by means of straight line forming the triangle by representing the vertex by means of the rain gauge. Now what we will be doing? We will be doing the perpendicular bisector to each side. This way we will be drawing the perpendicular bisector. Each and every rain gauges will be connected by means of straight lines forming different triangles, and the perpendicular bisectors of each side of the triangle will be drawn. Thus, each entire catchment will be divided into a number of triangles and Thiessen polygons. This way, here in this case we are having 3 Thiessen polygons. Now what we will be doing? We will be computing the representative area for each gauge. So, for this particular area, that is area 3, this is the rain gauge, that is P3 is the rainfall from the rain gauge in region 3, and we will be computing the representative area of that particular Thiessen polygon. In this way we will be having A1, A2, A3 areas. Depending on the number of Thiessen polygons developed, we will be having more areas. After that what we will do? We will assign a weight or weightage for each rainfall area, that is each Thiessen polygon area will be divided by the total area of the catchment. Ith Thiessen polygon area is AI, and that will be divided by total area to find out the weight corresponding to ith Thiessen polygon. Now, we can compute the areal average rainfall by using the formula P bar is equal to average precipitation equal to 1 by A summation of sigma I is equal to 1 to n AI Pi. A is the area represented by ith polygon, Pi is the rainfall recorded at the ith rain gauge, and P bar is the average aerial rainfall in the catchment. So, by making use of this formula, we can get the average aerial rainfall from the catchment. So, here in this case what we are assuming, each and every Thiessen polygon will be representing an area which is having the rainfall obtained from the corresponding rain gauge, which is within that particular Thiessen polygon. The weightage assigned in the case of arithmetic average to each of the station is same. That is what we were doing in the case of arithmetic average, P1 plus P2 plus up to Pn divided by n. So, the weightage which was given in the arithmetic average method was 1 by n. And in the case of Thiessen polygon method, it is Ai divided by A. So, here a representative weightage in terms of total area and the area of the Thiessen polygon is utilized. But in the case of simple average arithmetic average method, the weight is only depending on the number of rain gauges, that is 1 by n. So, from this itself you can clearly understand that Thiessen polygon method will be giving better result compared to simple arithmetic average technique. Better method is Thiessen polygon than the arithmetic average method. Now, there are certain disadvantages as far as Thiessen polygon method is also concerned. Let us see one by one. This method is not flexible as new Thiessen polygons need to be constructed every time. That is, in a particular watershed, we are having n number of rain gauges. So, based on the number of rain gauges, how we have proceeded? We have connected the rain gauges by means of straight lines forming triangles. So, in case one particular rain gauge is not in a working condition, that rain gauge has to be replaced soon. Otherwise, we have to go for constructing new Thiessen polygon network by omitting that particular rain gauge which is not under working condition. So, this is a disadvantage. Every time constructing the Thiessen polygons is not an easy task in a very large catchments. Second one is that it is not accounting the orographic influence on rainfall. Orographic rainfall where it is occurring in the hilly or mountainous region. So, the type of area is not coming into picture. Depending on the topography, features of the area, the types of rainfall which we are experiencing are of different types. So, here a weightage corresponding to the Thiessen polygon area and the total area, weightage is provided to a particular area by taking into account of the total area of the catchment and the area of the individual Thiessen polygons. But there we are not incorporating any effect of the type of precipitation, that is during the, if we are having a hilly terrain, then also we are making use of the weightage like this Ai divided by capital A. So, it is not differentiating between the different types of rainfall. So, this method is not applicable for the orographic precipitation. Next method is the isoheightal method, that is the third method. What is an isoheight? Isoheight is a line joining points of equal rainfall. For example, you might have done the course of surveying as a basic civil engineering course, you might have done the surveying course. In that course, you might have studied the line joining points of equal elevation, contours you have drawn. In the similar way, isoheight is a line joining points of equal rainfall. So, let this be a catchment. We are having rain gauges P1, P2, P3, and isoheights are constructed using the observed rainfall depths at these gauges and interpolated between the adjacent gauges. These rain gauges will be giving you the rainfall data, and we will be drawing the contours which are having equal rainfall magnitude. How we are going to draw? We are drawing the contours by means of points connecting the equal rainfall data. So, that way we are getting different isoheights within the catchment. So, that I am representing by means of notation I minus 1, I plus 1. Let the first contour I minus 1 contour is representing a rainfall of 4 centimeter. Ith contour is representing the 5 centimeter rainfall, and I plus 1th one is representing 6 centimeter rainfall. Now, the area AI is the notation which I am using for area between each pair of isoheights within the catchment. That area is measured or computed. We are having different areas between each isoheight like this A1, A2, A3, A4. Based on the data which is provided by the rain gauges, we will be connecting the points which are having the equal rainfall depth, and that way we will be producing the isoheights. Between two consecutive isoheights, we will be having certain area, that area can be measured. Now, what we will be doing? We will be assuming, let Pi be the average rainfall depth of the two boundary isoheights. That is, we are having the ith isoheight, and let Pi be the average rainfall depth corresponding to that isoheight. Area bounded by two isoheights between ith and I minus 1 contours we can calculate by using planimeter or by any other technique, computerized technique. We can calculate the area between two isoheights. Now, the precipitation within that particular area or the rainfall within that particular area can be averaged out by using the rainfall at I minus 1th isoheight and ith isoheight, that is Pi is equal to Pi minus 1 plus Pi divided by 2. So, this is the I minus 1th isoheight and this is the ith isoheight. So, 4 centimeter rainfall is there in the I minus 1th isoheight, and ith isoheight is representing 5 centimeter rainfall, and within this area A2 we will be having an average rainfall of 4 plus 5 divided by 2, that is 4.5 centimeter rainfall. So, P1 in the first region, that is P1 is given by 3.5 centimeter, P2 is given by 4.5 centimeter, and P3 is equal to 5.5 and P4 will be 6.5 centimeters. So, this way entire catchment will be divided depending on the rainfall data which we are collecting from the rain gauges. Points having the same rainfall data, equal amount of rainfall data will be connected together to form the isoheights. So, that way entire area will be having n number of isoheights. Each isoheights will be having, two different isoheights will be having an area between them. So, the area, the average rainfall corresponding to the intermediate area can be calculated by averaging out the rainfall data corresponding to those two isoheights. So, P bar is given by sigma I is equal to 1 to n Pi Ai divided by capital A. Pi we are calculating corresponding to ith and I minus 1th isoheight, and Ai is the corresponding area within those two isoheights. In the similar way, corresponding to the entire catchment, entire area, we can get the average rainfall by making use of this particular formula for average rainfall value. that is sigma I is equal to 1 to n pi ai divided by a. This is really an accurate method because we are not checking whether the area is plain area or hilly area, that is not coming into picture. It is based on the depth of rainfall data. So, whether it is orographic precipitation, whether it is convective precipitation, whatever be the type of precipitation, it does not matter. We are looking into the data corresponding to the rainfall. So, the effect of orographic influence is taken into account by means of the rainfall data. So, it takes into account of the rainfall in the particular area. That itself is taking into account of the orographic effects, because orographic precipitation at the hilly region is incorporated. Whatever be the area, even though directly area is hilly or mountainous, we are not taking into account, but the rainfall from the orographic precipitation is taken into account. Based on that, we are averaging out the values here. The last method which we are going to discuss in this lecture is the reciprocal distance squared method. That is, in this method what we are doing, in a catchment we are having n number of rain gauges. Certain location will be there where it is ungauged, we do not have any rain gauge. So, we will be calculating the rainfall based on the existing rain gauge data. That is to find out the amount of rainfall at an ungauged point in a catchment from the rainfall data measured from the rain gauges present in the catchment. The effect of rainfall from a gauge point on any other point in the catchment is inversely proportional to the square of the distance between the two. That is, we are having a particular point which is ungauged and another location we are having the rain gauge present. That is, we are having the points x1 represented by Cartesian coordinate system. You can consider point x1 and point x2. x1 is represented by x1 y1 and x2 is having coordinates x2 y2. How can we determine the distance between these two, capital X1, X2? That can be represented by capital D. It is given by under root of x1 minus x2 all square minus y1 minus y2 all square. And after that, what we will do? We will square it and we will take the reciprocal of that particular value. It is denoted by W. W is equal to 1 by D square. Now, we can get the average rainfall value by using this formula, that is P bar is given by sigma I is equal to 1 to n Pi Wi divided by sigma W. What is this capital W? Capital W is the reciprocal of the square of the distance between the rain gauged point and ungauged point. So that by making use of this, we will get the rainfall data within that ungauged area. So, rainfall interpolation, that is, this is a sort of interpolation technique. Different interpolation techniques are there incorporated in GIS software such as kriging. Different types of averaging interpolation techniques are available. So, that way whichever is giving the accurate value, by validating the method you can make use of it for calculating the average rainfall over a particular area. So, even though we are measuring the rainfall at a point by making use of the rain gauges, that can be converted into representative average aerial rainfall values based on these techniques which we have seen now. So, we have here in this particular lecture, we have seen very commonly used 4 methods, that is simple arithmetic average technique, Thiessen polygon method, isohedral method, and last one reciprocal distance squared method. Any of these methods can be utilized depending on the area. That is, if your area is flat and it is not very large, enough number of rain gauges are present, representative rain gauges are present. So, simple average rainfall can be, arithmetic average can be calculated by using the arithmetic average method. And you can go for Thiessen-Polygon method better than that of arithmetic average method by giving the weightage to be AI divided by total A. After that, in that we have found that in that particular Thiessen-Polygon method, we are not giving any emphasis to the type of rainfall, that is orographic precipitation is not given any specific importance there. So, that effect is nullified if we are making use of Thiessen-Polygon method. So, in that case you can make use of isohydral method. There we are making use of the rainfall data from the rain gauges and we are drawing the lines which are having the equal rainfall depth, which are termed as isohyds. So, isohyds will be drawn by making use of the rainfall data obtained from the rain gauges. So, these rain gauges will be giving us the values, whether it is convective or orographic, that does not matter. Based on the emphasis is given to the rainfall data. Based on that, the isohyds are produced and the area between two consecutive isohyds will be considered to get the average precipitation or the average rainfall within that area. And after that, combining all the rainfall data within the isohyds and the corresponding areas, we can get the total average aerial rainfall in a catchment. Then we have seen the reciprocal distance squared method for getting the average rainfall by using this particular formula. So, here I am winding up this lecture. You can look into these textbooks for getting more knowledge about the detailed knowledge about the different methods for finding out the average aerial rainfall. Thank you very much.